Hi, my name is theorize, and I'm an astrophysics major at the University of Florida. For my undergraduate research, I am investigating ammonia masers in the W51 star-forming region. So, W51 has some of the most active and brightest star-forming regions in the galaxy. This nebula has numerous astrophysical masers that astrophysicists theorize that these masers can probe stellar processes such as outflows, disks, and other processes. So, masers are essentially very extremely bright spots of emission caused by non-thermal excitation of molecules. So what this means is that when you're observing a maser, you can measure a very high brightness, but that very high brightness does not have any thermal properties, so you cannot measure the temperature of this maser. So these masers are caused by it can be caused by certain objects within the star-forming region. So this is what this is part of what this project is about. So what this project is about is that what we want to do is measure where the masers in W51 are occurring, and if that's near outflows, disks, or stellar or other stellar processes, and this can also be used to measure or investigate. This can also be used to investigate relationship between the velocities and brightnesses of masers and the high mass stellar accretion. So in the top right image, or just the top image, that's an image of the Spitzer. That's a Spitzer image of the W51, and it just gives an overview of how W51 looks. On the bottom left, that's W51 North. It's a ALMA image. It's from the telescope ALMA, and it's 3 millimeters in frequency, and it displays the continuum emission of W51 North, and it's produced by dust emission and free emission. And on the bottom right, it's a video that I made of one of the masers I found in W51 North, and that shows how bright these masers can get in respect to the environment. So the methods I use for this research project is CASA, which is called the Common Astronomy Software Applications, and I use CASA to apply the T-clean algorithm to the data I get from the VLA telescope, the radio data in the K-band, and I use T-clean to get better observations and measurements. I use Carter to view those images and to make points on where the pixel location is for each maser. I use Spectral to compare my observed frequencies of each maser to the masers, or not the masers, but the chemical transitions in the database, and this will allow me to measure the rest frequency, to find the rest frequency for each maser, and other intrinsic properties. Spectral Cube and PySpecKit are Python libraries that allow me to open cube files and fit 1D Gaussian curves to the spectrum of each maser respectively. And AstroPy is a well-known astrophysics Python library that I use to do various astrophysics tools, including, more importantly, the 2D Gaussian fitting. So, just a little, the small rundown on how cube files work. So, cube files, think of it like a cube full of different sheets, and each sheet has its own channel. This is its own channel, and with each channel that has a specific frequency that the radio telescope, like the VLA or AMA, would basically see and record. So for each data set I get, it's essentially a cube of different frequencies that I can look through and find the maser or the ammonia transitions for each maser. And on the left, you can see a plot that I made, a video that I made, going through each channel, and each channel has its own data to be recorded. And you can see on the left, far left, the ammonia transition, one of the ammonia transitions for W51 North, for a maser in W51 North. So spectral fitting. I use SpySpecKit again, and I used to fit the 1D. I used to use SpySpecKit to fit 1D Gaussian curves, and what this allows me to do is allow me to measure some of the spectral properties like brightness, the width of each Gaussian curve, the frequency, and their respective errors. And also, additionally, the low residuals that I get from this for each Gaussian fit allows me to know that I fit a good Gaussian fit. So low residuals indicate better Gaussian fits. So for spatial fitting, it's a similar process to spectral fitting, but I also measure the spatial location using AstroPy's 2D Gaussian function. So what this allows me to do is accurately measure the location of each maser. Measure each location of each maser, and that allows me to put each maser in a catalog, so I can compare to other datasets and research articles. So here is a comparison between my data that I've preserved and Henkel's data, and we're both looking at ammonia masers in a W51 North region. And for each transition, you can see that there's a noticeable shift in velocity, or VLSR, the local standard of rest. And what this tells us is that over time, the masers have moved. There's motion within each maser. So that's really important to note. And there's also a noticeable difference in the brightnesses for each maser transition. So this tells us that if the masers are moving, let's say in a disk, it can tell us that the masers are radiatively pumped, meaning that radiation from the star forming region changes whenever the maser moves, and that causes a decrease in brightness. So here is a comparison it's essentially a catalog so far of all the masers that I have observed in W51. And on the far left is an overview of a part of W51 North. And on the top right, you can see that there's actually three main areas that different transitions of masers are in. There's kind of like three spots that the transitions are clumped up in. And if you notice that for each color points, you can see that there's even parts of the maser spots. This maser spot is called W51D2, by the way, and it's a hypercompact H2 region caused by free emission, and there's actually within different peaks of the same transition, there's also different locations. So this is also important to note. And on the bottom, you can see there's a major spot that is unnamed at this point in time, and you can kind of see that there's also two different areas within that major spot to look at. So here is the correlations with velocities and brightnesses. The main takeaway is that we wanted to showcase the relationship between VLSR, the change in VLSR between my data and Henkel's data, and the rest frequency, the brightnesses, and the width of each spectral Gaussian line. So on the far left, you can see that there is really no correlation between a change of VLSR and the rest frequency, and that basically shows that with each measure that there is a varying change in velocity between my data and Henkel's data. So this is something to note, that the measures are indeed moving. And for the second plot, it shows a relationship between the change in VLSR and the change in brightnesses. So this can tell us exactly, give more insight of whether the measures are radiatively pumped, and if the measures receive less radiation over time between my data set and Henkel's data set. And the last plot showcased a direct correlation between the measures. It appears that essentially what this plot means is that Henkel's data appears to be more broad in the width, the V1/2 or full width half maximum of each Gaussian curve, and that essentially tells us that Henkel's data could have a lower spectral resolution than the data set that I have. So his data set may be more more broad, and my data sets are more narrow overall, which allows for more precise measurements. So these are something to look at, but as I add more measures to the catalog. So that brings me to my future work. So one thing that I want to work on in the future is to investigate exactly where the measures are in relation to different astrophysical processes and stellar processes, such as outflows and disks. Find the direction of each measure. So essentially, with the velocity, find the direction of where the measure is going in relation to the star-forming regions. Investigate what properties or what objects are creating the measure and influencing the measure, and if so, if there's an object creating the measure, what are the properties of that object? And lastly, to complete a full catalog of the different Ammonia measures and other measures that I may find in the VLA radio telescope dataset that I have, and W51 North and W51 IRS, which is another subset of W51. So thank you for listening to my talk, and I hope you enjoyed.